SwayamPrabha. Digital India. Educated India.
Good morning, everybody. Today we will start a new topic on finite volume method to solve three-dimensional Navier-Stokes equations in complex geometry. Here the assumptions are the following. Flow is incompressible, it is unsteady flow, laminar. Of course, laminar assumption per se, it has been mentioned, but even if the flow is turbulent, we can use the same algorithm through appropriate turbulent flow models, to appropriate turbulence models, and there are ways to handle the issues of turbulence, but the same algorithm can be enhanced. But right now, maybe for the purpose of it, we can say that flow is laminar, and constant properties, all the properties are constant. Basic features, this is applicable to three-dimensional problems, and the grid is such that elements are all non-orthogonal hexahedrals. Basically, in order to mesh a geometry, the body-fitted coordinate is used, and the grid meshes are such that it fits in the geometry appropriately. While doing so, the individual elements, those are hexahedrals with different sizes and different orientations. And here we will use collocated grid arrangement. That means all the dependent variables U, V, W, P and temperature will be defined at the same location at the center of the cell. A basic version of this algorithm was presented by Professor Ishwaran and Dr. Satya Prakash in a conference at Bangalore, and this version was developed by Professor Ishwaran and Dr. Satya Prakash completely indigenously in 1998. Later on, some work was done and work is still going on for further improvement. I will mention about those aspects at the end of the lecture. Now, governing equations are obviously, first equation comes continuity equation, that is divergence of velocity vector in a flow field is 0, and in an element, of course, it is 0, and we have written volume integral of divergence of velocity vector over the control volume of interest equal to 0. Then we have converted that volume integral into surface integral. Now, general transport equation, this equation 2 is basically Navier-Stokes equations in 3 dimensions, and it can be representative equation for the scalar transport, that means for temperature or for energy transport as well. And we have written the generalized form. As you can see, this is basically del T of rho phi over the control volume, and then this is basically divergence of rho velocity vector into phi minus this is diffusion coefficient gamma phi, and again grad operator dot grad of phi. Basically this will produce something like del square phi type of terms together with diffusion coefficient. It is basically the diffusion, either momentum diffusion or energy diffusion, and it is integrated over the volume of interest, and this is the source term. So this is the generalized way of writing this. Here we combine the convection and diffusion part so together, and evaluate this volume integral through the surface integral, basically the confining surfaces, and we apply the lumping, mass lumping here. So basically this del T, when it is applied over rho phi, it is integrated over that volume, and as you know that integration of rho dV is basically mass, and into phi it is del T of that quantity, and this source term as you can see in the Navier-Stokes equations, x, y and z direction, or three perpendicular directions, it is grad of phi dot n dV. So pressure gradient forms the source term. Similarly, we'll have to write corresponding source term in the energy equation when we reuse this equation as the energy equation. So Ni is a unit vector in the direction of the velocity component uy. Now the control volumes I have already mentioned are defined by the coordinates of their vertices. You can see 1, 2, 3, 4, then 5, 6, 7, 8, coordinate of their vertices, which are connected by straight lines. So as you can see, 1, 2, 2, 3, 3, 4, 4, 1. Similarly, 5, 6, 6, 7, 7, 8, 8, 5. These are connected through straight lines. The coordinates of control volumes are calculated by the grid generation technique. A collocated grid arrangement is employed. The dependent variables u, v, w and p are defined at the same location, the centroid of the control volume shown in the figure. The centers of the 6 neighboring control volumes, so center of this control volume is P, and centers of the neighboring control volumes, if you imagine another control volume on the eastern face, center of that control volume is E, uppercase E. Similarly, if there is another control volume just on the western side of it, center of that control volume is given by uppercase W. Similarly, uppercase N, uppercase S, uppercase T and uppercase B. So for the east, west, north, south, top and bottom neighboring control volumes. The phase center points, here we can see that phase center point of eastern phase is given by lowercase e, and the western phase also it is given by lowercase w. Similarly, lowercase n, lowercase s, lowercase t and lowercase b are located at the corresponding phase centroids of the control volume of P. The edge centers, like if you consider this as one edge or this side as one edge, so they are also the center of the edges are called as, for example, here it is TE, and this center is given by BE. Similarly, this center of the edge is given by NE. And so when we go for IJK indices, then this is the cell of interest we are calling P cell. So the indices are IJK. So IJK cell is basically the P cell. Similarly, eastern neighbor cell which will located at the the eastern neighbor, it will be identified as I plus 1 JK. Western neighbor, that cell is identified as I minus 1 JK. Southern neighbor will be identified as I j plus 1k. J is basically, as you can see, J is in this direction and this is increasing J direction. So I j plus 1k. Northern neighbor is I j minus 1k. Top neighbor is I j k plus 1 and bottom neighbor is I j k minus 1. And east-west direction variation is the variation in I. As you can see that eastern side I is increasing, I plus 1, I plus 2, and western side I is decreasing, I minus 1, I minus 2, etc. Similarly, J is in north-south direction. So J is increasing in southern direction, J plus 1, J plus 2, etc. J will decrease in northern direction, J minus 1, J minus 2, etc. And K is in top and bottom direction. So basically K plus 1, K plus 2 is in the top direction, and the bottom direction it will be K minus 1, K minus 2, etc. So that is basically the grid topology. Now we'll discuss how to calculate the volume of hexahedrals and the volume of tetrahedrons. This is a very important aspect, and this topic was discussed in detail in a very well-known, referred paper of Cordula and Vinokur, which was published in AIA journal in 1983. Now let us consider a general hexahedron defined by 8 arbitrary corner points, like 1, 2, 3, 4, 5, 6, 7, 8. Now this hexahedron can be divided into 5 tetrahedrons, right? Five tetrahedra, and we can calculate volume of each tetrahedron. Like here we can divide it in such a way that we can get the following tetrahedra. One is given by 1, 4, 3, 8. Another is given by 1, 6, 5, 8. Another is given by 3, 6, 7, 8. So it is clear. One is given by 1, 4, 3, 8. Another is given by 1, 6, 5, 8. Another is given by 3, 6, 7, 8. So these three plus two more, those two more are 1, 6, 3, 8. 1, 6, 3, 8 is 1, 1, 6, 3, 8. Another is 1, 6, 3, 2. So these are the 5 hexahedrons, and we know how to calculate volume of such hexahedrons, that is written here also. It is given by 1/6 of the triple product of the 3 vectors emanating from one of the vertices and ordered according to the right hand directions. For example, how to calculate volume of tetrahedron given by 1, 4, 3, 8, and it is then according to what we have written, it is triple product, that means and triple product of the vectors emanating from one of the vertices. So from 1, the basically the vectors are then we can say 4, 1, 3, 1 and 8, 1. So triple product of R4, 1, R3, 1 and R8, 1 divided by 6 is the volume of the tetrahedron 1, 4, 3, 8. So it is given by 1/6 of the triple product of the 3 vectors emanating from one of the vertices, and the vectors are defined as Rij equal to Ri minus Rj. So we can write then 6 times volume of 1438 equal to R41 multiplied by R31 into R81. So this way, if we can calculate individually the volumes of 5 5 tetrahedra, then we will get the total volume of the hexahedron. Now, following this, 2 more short discussions, but as I said, this Cordulus paper is very important paper, and many of you may be interested in that, I have given the reference. Please try to have a look at the paper and read the paper if possible. The surface vector S5678, whether you calculate here S5678 or S5678, in figure is independent of the choice of the partitioning surface diagonal. See, once we have partitioned it this way, this 6,8 is the surface diagonal. At another instant, we have partitioned it this way, 5,7 is considered as the surface diagonal. Basically, independent of the choice of the partitioning surface diagonal needed to uniquely define the volume. Thus, expressions can be written as, so S5678, we have given the expressions like, 0.5 into R75 into R68, and there are all these options are possible, and these are independent of dividing the surface by the diagonal, whether this diagonal or this diagonal, we can get these expressions, and they mean basically S5678. So finally, what is very important for us, that for some such arbitrary hexahedral, how to calculate its volume, and we have written that you can bring 6 to right hand side, that then volume will be R71 by 3. 71 means this diagonal which connects point 1 and 7, R71 into surface area 1485, this surface 1485, plus surface area 1234, that means this surface base with respect to this particular hexahedral, and plus 1562, that means this surface. So basically this diagonal emanating from 1 and 3 surfaces that are also emanating from or connected with 1. So one surface is 1485, another surface is 1234, and another surface is 1562. So having known this, if we come back to our hexahedral that we have already defined, we can calculate different surface areas like eastern surface, western surface, northern surface, southern surface, top surface, and bottom surface. So these expressions have been given. This surface area of eastern face is given by half R74 into R83. Similarly, surface area of western surface is given by half R16 multiplied by R52. Northern face, this is the northern face, given by half R27 multiplied by R63. Southern face is given by half, surface area is given by half R18 multiplied by R45. Similarly, top surface ST is given by half R75 multiplied by R68, and the bottom surface is given by half 13 into half 24. And then just following our previous slide, the volume occupied by this particular arbitrary control volume is 1/3 of R71, exactly what we did in the earlier slide, R71 multiplied by surface area of the southern surface. That means 1485 plus surface area of the bottom surface, that means 1234, plus surface area of the western surface, that means 1265. So this is how we will calculate the geometrical parameters. We will see these are extremely important, and we will need this at every step of our calculation. Now, for an incompressible flow of Newtonian fluid, already we have written this. The general form of governing equation we can write del del T of volume integral phi dv plus surface integral. U is a vector quantity, so uppercase U phi, minus gamma phi, this is the coefficient of transport, momentum transport or thermal transport. In the case of Navier-Stokes equations, it is coefficient of viscosity by rho into grad phi dot ds surface vector equal to 1 by rho. This is the source term integrated over the volume S phi. And the source term, for when we are considering this as momentum equation, then source term will be the pressure term. So this is 1 by rho surface integral of P into I. I is unit tensor. It will be given by 100010001 dot ds. Now the variables, so this is, we are calling this as general transport equation because the same equation can be used for continuity, momentum, and basically energy. When we consider continuity equation, then basically phi will be 1, and this term and these two terms will be 0. In order to make them 0, that gamma phi is 0, S phi is 0. When it is momentum equation, this phi will be U, V and W, and gamma phi will be mu, coefficient of viscosity, and S phi will be del P del X for X momentum equation, del P del Y for Y momentum equation, and del P del Z for Z momentum equation. And for the energy equation, phi will be T, and basically this gamma phi will be K by rho Cp. K by Cp, because rho is already there. This term has to be K by rho Cp, so already rho is there, so gamma phi has to be K by Cp. Now again, let us refer to the general equation 2 and try to get the expression for continuity equation. So in order to get the expression for continuity equation, we have to substitute phi equal to 1, and we have also seen that source S phi will be 0, and the coefficient of diffusivity, that means gamma phi will be also 0. So only the first term will be there, which will contribute as surface integral of rho u dot ds. And that means in this case, it is basically summation of rho u dot as on J surface, whereas J means eastern, western, northern, southern, top and bottom surfaces. So it is summation over J uj dot sj. Sorry, uj dot sj. Now sj is the surface vector representing the area of the ith cell face, and uj is the velocity vector defined at the cell center of J or J surface. The discretized form of continuity equation in terms of the fluxes through surrounding surfaces of the control volume then will be summation of Fj, which means Fe plus Fw plus Fn plus Fs plus Ft plus Fb. And this summation, obviously there will be no mass accumulation or no mass deficiency, will be 0. So where Fj is the outward mass flux through face J defined by Fj equal to uj dot sj, and this u is vector, so all the components of the velocity, and sj is the surface vector representing all the surfaces, each one of the surfaces. So we can write Fj equal to rho uj dot sj, and we can further explain it that the surface vector has components in more than one Cartesian direction. All the velocity components contribute to the mass flux. So each Cartesian velocity component is multiplied by the corresponding surface vector component. So each surface vector will have components in 3 Cartesian directions, and we have 3 Cartesian velocity components. So that is why each Cartesian velocity component is multiplied by the corresponding surface vector component, projection of the cell face onto Cartesian coordinate planes, and then we evaluate this. In this way we evaluate Fj equal to rho uj dot sj. Now we go to the convective fluxes. Now surface integral over convection flux of variable phi can be approximated in the form that this is also through all the confining surfaces. So integral over the surfaces rho u phi dot ds. So that means summation over j rho phi j into u dot s j, which again if we plug in our f definition we will get fj into phi j over each j, and then summation, where fj is the mass flux through face j and phi j is the value of phi at the center of the cell. This phi can be any quantity that can be convected. So it can be 3 velocity components, u, v, w, it can be temperature. So this is how we define summation fj phi j. So integral as rho u phi dot ds, we can write this now. Then fe into phi e, fw into phi w, fn into phi n, fs into phi s, ft phi t plus fb phi b. All are summations. Here, for example, phi e is the interpolated value. See, e is the midpoint of the eastern, small e is the midpoint of the eastern cell face. So phi e is the interpolated value of the variable phi at the center of the east face. This interpolated value can be evaluated very simply by taking a central difference, which is basically linear interpolation between the neighboring cell center values. That means the cell of interest we have already defined is P, and at the center phi is phi P, and eastern neighbor at the center phi is defined as phi E. So for example, at the east face, that means phi E defined as the center of east face, and this will be interpolated with the or using the values of the phi defined at the cell P and phi defined at the cell E, eastern neighbor. So phi E, this is linear interpolation but central difference, we can see. So VE, volume of eastern neighbor, divided by volume of eastern cell plus the cell of interest P into phi P, plus volume of P, cell of interest, divided by total volume, that means volume of E and volume of P, into phi E, whether phi is defined at the center of volume E and phi P is defined at the center of volume P. So this way we can do the basically taking either side of the cell face and do the linear interpolation following a central difference philosophy. So phi E equal to V, we have written it again, divided by V plus Vp multiplied by phi P plus Vp divided by VE plus Vp multiplied by phi E, where VE and Vp are volumes of cells enclosing the points E and P respectively, and phi E and phi P are the values of independent variable phi at these points. That's what we are explaining. So basically the eastern neighbor volume of that cell is VE and phi E is defined at its center. Cell of interest volume is Vp and phi P is defined at its center. And this is where at the eastern cell face center we define through the interpolation. Since all the dependent variables are defined at the same location in the collocated grid arrangement, exactly same expression or same interpolation scheme will be used to express all other dependent variables. That means u velocity, v velocity, w velocity, P, all the quantities will be interpolated, can be interpolated following this philosophy. However, the use of center difference approximation mentioned above to compute the convection fluxes may lead to numerical stability problems. That we have seen earlier also, that central difference sometimes for high velocity flows can give stability problem. Therefore, the convection flux is split into two parts: a first order upwind difference scheme, we are calling it UDS, and another part which equals the difference between central difference and upwind difference approximation. So upwind difference scheme plus difference between central difference and upwind difference. So that means Fe phi E, Fe into phi E upwind difference plus gamma into Fe into phi E central difference. Central difference will be exactly like this, minus Fe into phi E upwind difference. And upwind difference means in the differentiation will involve the upstream point if the depending on the direction of the velocity. So now from this philosophy, Fe phi E, what we have written here, if we want to write it in computational algorithm, then we have to write phi P within this bracket Fe comma 0 minus phi E within this double bracket minus Fe comma 0 plus gamma. Gamma is a fraction and multiplied by this central difference minus, we are calling this upwind difference. Now if you look at it typically, this will involve upstream point depending on the direction of the velocity, and that is why this special symbol has been used, which is double bracket. And this double bracket means if we write PQ inside a double bracket, which will mean greater of the two, right? So velocity can be negative. In that case, this will be minus Fe will be greater of the two. So, and if it is positive, then obviously it will be greater of the two. So this will eventually decide the direction, depending on direction of velocity, will involve the upstream point phi P or phi E, and this is the central difference. So you can see this symbol double bracket has substituted when we defined this, if you recall that involvement of upstream points through the modulus sign. In several schemes we have done so far, we have done that. So, and it is just equivalent to that. Now Fw into phi W, following the same philosophy, this is basically central difference, and this is different. This is basically upwind difference, and this is basically a factor multiplied by central difference minus upwind difference. Same here, this is upwind difference, this is a factor multiplied by curly bracket is getting closed here. Inside we have central difference minus upwind difference. So this is flux at eastern surface, convective flux as western surface, convective flux as southern surface. In the same way, just you have to follow the expressions and look at how we have applied upwind differencing by involving upstream point Fn phi n, Ft phi t and Fb phi b, bottom surface, top surface, northern surface, and everywhere basically we have taken UDS plus central difference minus UDS, minus upwind difference scheme. So this is how we can compute the convective fluxes. If a fully implicit method is used for time stepping, the upwind parts of the above equation are implicit and they are incorporated in the coefficients of the unknown velocity during pressure velocity iteration. This I will explain again while doing the pressure velocity iterations. The central difference terms, on the other hand, are evaluated using previous iteration values and are used as source term on the right hand side of the same equation. This is the so-called deferred correction approach. If you recall our first preliminary few lectures, when we introduced finite difference, finite volume methods, we referred to this scheme, very well-known scheme, Khosla and Rubin's scheme is called deferred flux correction approach. Professor Prem Khosla and Professor Stanley Rubin, they formulated it. Multiplication of the explicit part, I have already mentioned. This is a fact, this gamma is a factor which is basically a fraction. So this factor gamma, which lies between 0 and 1, allows the introduction of numerical diffusion. If gamma equal to 0, this means pure upwind differencing. If gamma equal to 1, means pure central differencing. So here basically we have to, since if you compare it with the schemes we used for simple or MAC, they are also used something like alpha, which varied between 0 and 1, but there when it was tilting towards 0, it was getting closer to central difference. When it was tilting towards 1, it was shifting towards upwind difference. Here it is just little different. When gamma is 0, it is upwind difference, pure first order upwind, and gamma equal to 1 is pure central difference, second order central difference. So for higher accuracy, we can go for gamma which is on the side of 1. The deferred correction approach enhances the diagonal dominance of the coefficient matrix. When we'll arrange this pressure iteration matrix, we will again discuss it, but it's better to mention here now that deferred correction approach enhances the diagonal dominance of the coefficient matrix, which adds to stability of the solution algorithm. So we have discussed today about the discretization of the continuity equation following finite volume approach on arbitrarily shaped hexahedral, and also we have discussed about calculation of convective fluxes. In the next class, we will take up diffusive fluxes and setting up the pressure velocity correction scheme, and we will discuss about the complete solution algorithm. Thank you very much. Thank you.